Okay, can we start?
Yeah.
So, questions. Anyone looked at the preset? Questions on that? Nope.
Can we paste
Yeah, you can. I mean, I've always allowed that, so sure. Any other questions? Okay. Folks sitting at the back, be social, come up.
for wrong majors?
At least you get to know me in the winning days of the class. Come on. So some of you expressed concern about the repeated extensions I ended up giving, and I kind of provided kind of my perspective on it. So yes, I could have handled it better. You are right on that front. At the same time, put yourself in my shoes. Didn't want a class where if I had stuck to the original deadline, at that time, by my count, there were 2 or 3 students who had any semblance of the thing working. Okay, so all of you benefited from at least one extension. Don't begrudge other extensions to your classmates. Okay, I think from my perspective, I wanted to make sure that every student got a chance or a sense of completion in doing this thing. Okay, and look, if you finished earlier, you're probably among the better students in the class. I'm sure you are doing better at all other elements of the course also. So one design assignment out of 3 design assignments, which in turn is a part of just a fraction of the course, it's not going to make all that difference. So calm down. That's all I would say. Having said that, I acknowledge I could have, should have handled it better. Perhaps did some sort of a graded thing where if you some sort of a penalty and extension with some sort of a reduction, I should have done that. Well, too late to do it, so just can't go back on that. So just my side of the story. I think all of you have benefited from the extensions, and look, in some other course, it may be the other way around. Okay, I think what also ended up happening was last week, from what I realized, many of the students had 2 or 3 midterms, and I just wanted to factor that in also. So just hopefully you will understand. If you don't, that's fine too. Okay, any other yeah, like someone said, you are not running the course, so well that's one of the luxuries I have, but I decided to kind of err on the side of just giving everyone the sense that I think the number of thankful emails overrode the one which were not. So yeah, I think I made both sides happy or unhappy, and that's the way it's going to be. Okay, go ahead.
I have a question about the spec. I mean, it's already too late to change it, but for the space in between characters, you said that, or the spec said that there's supposed to be three ticks of zeros. Does that mean 3 ticks of zeros in addition to the 0 from the end of the last more symbol, or is that 3 ticks including the 0?
Okay, I'm not sure I understand your question, but it's the 3 zeros or whatever three dit worth of right. I mean, whatever is your Morse code basic time unit, 3 Morse time units worth of zeros in between.
Like if you sent like E followed by A, you have like E is just dit, so it'd be 1 0, and then is it 2 more zeros before the first part of A?
So E is just a dit. So remind me, it's just a dit, right? So it's just a 0. So it's just a 0 for, sorry, it's just a 1 for one time unit. And then the next letter in between those, there have to be 3 zeros.
Okay.
Right?
So would we be penalized if we did dit as in like 1 0 and then followed by 3 zeros for the intercharacter space?
No, so dit and dash are both ones.
No, dot is 3 ones.
Dot is 3, sorry, dash is 3 ones and dot is a single one.
Yeah.
Okay, so both dot and dash are 1. It's just they differ in the duration of the time.
Right.
Right. So you seem to be saying that dot is a 0.
Well, because in order to tell the difference between the more symbols, you had to have a space in between them. So if you had like dit followed by dot, it'd be like 1 0 1 1 1.
Right. So let's say there was a letter which was dot dash. Okay, then that would be a cycle, and let's say n equal to 1. Okay, so 1 clock cycle of 1, 1 clock cycle of 0, 3 clock cycles of 1. Okay, that would have meant I have a single letter which is dot dash. If on the other hand, I had a letter which was just a dot and then another letter which is just a dash, then it would be one cycle of 1, 3 cycles of zeros because now it's the inter-letter spacing, and then 3 cycles of dash.
Okay, so
Okay.
If we interpreted it to be, there would be 1 cycle of 0 as a result at the end of the more simple, followed by 3 cycles of zeros for the inter-character gap.
No, but where is the 1 cycle coming from?
Just because the way that I constructed the logic was to put like a 1 cycle of 1 for the dot and then 1 cycle of space, so that the next element in the sequence would be able to do it without having to account for the space.
I mean, we'll certainly be cutting some points on this, not Morse code at that stage, all right? I mean, and I don't know whether you're applying it consistently in the sense that are you saying every dot is a 1 followed by a 0, or is it every dot is a 1 followed by a 0? Won't you run into some ambiguity there?
No.
Okay. Anyway, let's take that offline. It's something that just chat with Paul. I mean, it's not like we'll just deduct everything either, but of course you went away from the. So the part which we will be tolerant, as kind of I emailed around on Piazza, is the interpretation on the spaces themselves. Okay, whether the space is being transmitted as kind of you decided to make use of some unused Morse code to represent the space character versus whether you are using 7 zeros in a row as a space, and whether you are coalescing multiple back-to-back space into a single space versus retaining them. So those we will be lenient on. Yeah. Any other questions? Anything on anyone seeking to attempt the design assignment 4? No. No one. Well, okay. A few. Okay, cool. It's actually not that hard. It's a lot easier than design assignment 3, just to kind of. And other thing, the email that I sent around, okay, about you are not allowed to share Logisim modules. Okay, this is an individual design assignment. The other thing is, trust me, the design similarities go a lot deeper than what Logisim file looks like. Okay, so superficial attempt at hiding are not going to work anyway, and penalties are just way too severe. So don't attempt it. Okay.
For the design assignment 4, you said there's like 65% on the correctness, and then 35 for like
elegance.
Yeah, so like how.
And like I said, it's subjective. It's in a different context. One of your classmates, maybe you said you are not running the class, so I get to decide that. But it's basically going to be things like for example, you can have a really naive implementation where every operator is done separately versus you actually share logic. So elegance is going to be the way you structure the design, how compact it is. While I'm not asking you for a cost function, but we are pretty experienced in assessing whether it's an expensive design or a cheap design, things like that. So we're going to factor those things in.
If you get like 65 and a 0 in elegance?
Say it again?
You get like a correct, like if your circuit works, but your elegance
yeah, in theory you can, sure. You can get 65 for correctness and 0 for elegance, sure. By the way, also very likely than not, if the design is inelegant, you have a hard time getting it to work. So if it's a working design, I don't think it would be 0 elegant. Okay. But in theory, it's possible. Okay. Any other questions on that? Okay. The plan for today is, firstly, for those of you attending, there is another quiz. Okay, extra credit quiz. I'm going to quickly hopefully, as I had expected, you have all watched the video, but I'm still going to just recap a few of the definitions. So there were 2 notions of delays that I had introduced. One delay is, okay, I think I'm on the wrong slide. One delay is that, so this is about combinational logic, and there's one delay which is a propagation delay. And propagation delay basically says that from the last time an input changed to the last time the output changes. In a sense, from the point input becomes stable to the latest point output will become stable. Okay, and in this diagram, what you're seeing is that there's A is the input, B is the output. A becomes stable at time t3, and output B becomes stable at time t4. This gap from t3 to t4 is the propagation delay. And there are a couple of things why kind of what happens in this duration. One is that there are some gates where the delays may depend upon the actual value of the data input. Like for example, you might imagine that an inverter may propagate a change from 0 to 1 more rapidly than 1 to 0. Okay, and it can happen because inside there are two different kind of transistors and they may not have symmetric delays. So it's certainly possible that an adder, for example, may, given what the specific input values were, may add them faster in for one set of values, slower in another set of values. So what here when we are saying that T3 to T4, we have to really look at the worst case across all possible data input values. The other thing that we also dealt with was that A and B may be multi-bit signals, and it's possible that while one bit may settle very quickly, the other bit may take a long time to settle. So if I'm looking at all the bits of a signal, I would say the signal became stable when all the bits have become stable. Okay, so that could be another reason. So uncertainty in the values is indicated by this kind of a shaded hashed kind of drawing. So from T2 through T4, B has some unknown value. Okay, in the sense by unknown we mean it's neither the original value nor the new value. It's something in between. It started to change at T2 but has not yet stabilized. So propagation delay is last time inputs changed to the latest time output will change. The other delay, which was equally important, was contamination delay. It basically is saying how rapidly can the output get contaminated. So from the first point in time, the input changed. So one of the bits in the input changed, if it's a multi-bit signal, to the first time the output can begin to change. Again, across all possible data values. So it's possible that for some particular data value, my circuit is very rapid, and therefore the output begins to get impacted very quickly. So that's called the contamination delay. And then always our delay notation is in the subscript out here, the first letter is either C or D, indicating contamination and just plain propagation delay. Sometimes instead of D, I use P, but so it could be TPAB versus TDAB. And then A and B refer to the point. So I can define these delays between any pair of input and output. So that was one concept we had introduced. Another concept we had introduced was, let's see. Yeah, if I have two combinational logic blocks in parallel and in series, then kind of I can. So in case of series, the contamination delays add up. So for this overall assemblage, this is Amber Alert going on. Okay, so from the input to output for series, the contamination delays add up, propagation delays add up. In case of parallel, we have to, if I module like this, then I have to look for the shortest path that exists between the two, and that will correspond to the contamination delay. So I look at the shortest contamination delay over all the paths. So each, like in this example of parallel, both modules have their contamination delay. For the overall, the contamination delay will be the one which corresponds to the shorter of the two, and propagation delay corresponds to the maximum of the two. So by having this rule, then I can always create I can come up with contamination delay and propagation delay for more complicated assemblage. Another point I had made was that for basic gates, like a NAND gate and all, usually contamination and propagation delays are one and the same. There is a single delay number because these are such simple circuits. So in this particular case, for each one of the three gates, the number which is given is both the contamination delay and the propagation delay for the corresponding gate. And then to find the propagation or contamination for the overall circuit, we have to apply our series and parallel rules. So for propagation delay in this example, if I'm trying to find it between, let's say, A and F, then A can affect F through two paths. It can go through A top gate, D the OR gate, and F, or A can go through this bottom gate and then through the OR gate. So the delay through the bottom gate is higher, so that's why TDAF is 4. Contamination delay, we are going to look for the shortest contamination delay. So in that case, we'll go to the top one, 1 plus 1, 2. So more complicated circuits, and there I had several examples in the lecture, including this one of an adder. So let me. So this is what we had worked out, where this circuit really has two types of gates. One is the gate corresponding to a NAND gate, which is Q1 and Q3, and then the other primitive gate is this weird-looking structure, which is called OAI21, and that has a delay of 120. And there are three copies of that: Q2, Q5, and Q4. And then to find the contamination and the propagation delays, we basically come up with the min and the max between every pair of nodes. So these tables, what they're doing is, this is saying this is a min table, and it's telling me the minimum delay between, let's say, the columns correspond to the input, the rows correspond to the output. So what this table, for example, is saying is that from A to C out, the minimum contamination delay is 200. And from A to C out, the maximum propagation delay is 320, and so forth. And that, with that, we can come up with contamination delay and propagation delay for any pair of input and output. So this was applying the basic rules. The other very important concept that I had introduced was, and it was this notion, working with sequential logic, and kind of the concept being that if I have an edge-triggered flip-flop, what happens if the data changes around the same time as the clock is changing? And the answer is, if I look at a flip-flop in its most pure form, then what's doing is trying to sample the input D at an edge. And for that process to, just from a purely physical perspective, for that process to work, the data cannot be changing at the clock edge, because if I'm told to report on a phenomenon and the phenomenon is changing, then my report will be ambiguous. So for a D flip-flop to just physically do its job, there has to be a time window in which it is stable, a little bit before the clock edge and a little bit after the clock edge, in which the data is stable. So what this diagram is showing is that clock edge, sometime t sub s before that and sometime t sub h after that, the data is stable. So what you see out here is basically saying that the shaded means it's changing, we don't care, but in between the data has some value. I don't know what the value is, but it has some fixed value. And then again, it's just free to change after th. If it changes in this duration, then bad things happen. And I had some discussion on that, how the flip-flop can go into kind of this weird analog mode where if you put an oscilloscope, you will see noise and all. So T sub h, T sub h, setup time and hold time are basically saying how much before the clock edge should the data be set up, and how long should it be held stable after the clock edge. The other delay, two other numbers that we have with the flip-flops are how much is the propagation delay and how much is the contamination delay. Now, in case of a edge-triggered D flip-flop, if I change D, nothing will happen to Q until clock comes. So really the meaningful delays are with respect to the clock edge. So we basically see two delays, a propagation delay and contamination delay, which are from clock to output in either case. So TDCQ means that from the point the clock edge came, what is the latest time output will stabilize. And TCCQ means from the time clock edge came, and assuming the data was satisfying my setup and hold time, what is the earliest time data data output might change. And one other thing I would like to also point out is that it is possible that T sub h and T sub h might be negative in some cases, and I'll explain why that might happen. But basically what's happening is that given a T sub s, Ts and Th, there is a window around the clock edge. So let's say the clock edge came at time TCLK. Then from a time TCLK minus Ts to the time TCLK plus Th, where Ts and Th are both positive, during that time window, the data has to be stable. Now, and the other thing you can also say is that the second number has to be greater than the first number for all of this thing to make sense. If this is a time window, then it also stands to reason that TCLK plus TH is greater than TCLK minus TS. Or another way of saying is that T sub H plus T sub S has to be greater than 0. So if both are positive, that is certainly true, but one could be negative, and this could still be true if the other is positive enough. Both cannot be negative. Now, why might T sub S or T sub H be negative? So imagine the following scenario. Let's say I gave you a D flip-flop. It had signal clock. It had input D. It had output Q. And let's say I told you that it has TS of 3, and let's say it has TH of 4. Okay. And what this basically says is that from 3 let's say nanoseconds, 3 nanoseconds before clock edge to 4 nanoseconds after the clock edge, data has to be stable. But now let's say I decided that I'm going to make a new D flip-flop, which is just a repackaging of this D flip-flop, but where I put in a buffer on this clock line. Okay, so I have a new D flip-flop, and let's call it D prime, clock prime, and Q prime. All I did is I repackaged it, and I just said, look, let's imagine there is a buffer. And let's say, hypothetically, the buffer has a delay of 5 nanoseconds. Okay. Why might I put a buffer? Well, it may be my clock signal is too weak. I need to boost it up before I can drive this particular flip-flop, for example. Okay, any number of reasons. Okay, so buffer introduces a delay. Now let's imagine you don't know the internal details of it. I give you this new D flip-flop, the one which has inputs D prime, clock prime, and Q prime. My question, what would be its setup and hold time? Okay, so original, if I were to think from the perspective, so D is the same as D prime, Q is the same as Q prime. So really I messed up the clock. Okay, if I look at the original clock signal, then it basically said that from 3 time units before that to 4 time units after that, the signal has to be stable. That is how my original flip-flop was. But now let's say I added this delay, this buffer. So for the user of this outer flip-flop, the reference point is clock prime. So any setup and hold time have to be with respect to that. So my question is, what setup and hold time would you advertise for this outer flip-flop? Anyone wants to take a shot?
-2 and 9.
-2 and 9. So it satisfies the basic premise. The sum of the two have to remain the same. So -2 and 9 adds up to 7. Currently we add up to 7. So that's a good sign. Does anyone disagree, agree? If you agree, explain what's going on. Why is that? Okay, can anyone tell me what will clock prime look like? So let's say clock is the way I have drawn it. Is clock prime coming earlier or later? Earlier. Okay, so would its edge be earlier or later? It will be earlier. How much earlier? 5 nanosecond earlier, right? So if I were to draw clock prime, then it would look something like this. Agreed? And now if you see what is TS, remember TS says how much before the clock edge it should be stable. Well, if it is happening after, then that means TS has to be negative. So this thing is a setup time of -2, and this guy is 9. So that is why this this inner flip-flop has this spec, but the outer flip-flop will have specs of TS equal to -2 and TH equal to 9. And a quick check again is that the sum of the two should remain unchanged. Let's imagine I decided that instead of playing this game, I'm going to give you a different modification. This time clock remains unchanged, but I put a 5 nanosecond buffer at the data input. So now I have a new flip-flop where the only difference from the original flip-flop is that there is a buffer on the data line of 5. Would someone tell me what will happen now to set up and hold time?
Is it 8 and -1?
So the suggestion is 8 and -1. Any other? So again, it passes a smell test. 8 plus -1 is 7, so that it meets. Anyone from this side? The side seem okay? Agreed? Okay. So why is it working? Let's think about it. So what's happening? If D is being delayed, if D, remember, what we care about is the signal D out here. D prime comes earlier, so D comes later. And a later signal has to meet this requirement, right? So if I were to, so how late, how early, so think about it this way, how early should I come so that even when I'm delayed, I still meet the setup time? So if I come 8 nanosecond before the clock edge at D prime, then D will come 3 nanosecond before the clock edge, and that is what we care about. So setup, this is our new setup time, that has to be TS. And if I and likewise, how much hold time? Well, if I am if D prime is coming 5 before clock, then that means D is coming. If D prime has to remain stable for if D has to remain stable for 4 after the clock edge, but then that means that D prime can even change nanosecond before the clock edge, and then we are still okay because it is arriving late. So I can have a negative hold time in this particular case out here. So, but all that is happening is it's an artifact of what is surrounding my D flip-flop. Okay, the pure D flip-flop, which is unadulterated by all the surrounding logic, would always have positive setup and hold time. Okay, but because of wiring delays or buffers and stuff like that surrounding it, we may get modules which may have setup and hold times which are negative. Both cannot be negative, as we realize, but it's certainly possible one or the other may being negative. But it's purely an artifact of additional delays that we are seeing in there. Questions on this? Oh, okay. Okay, so so that was the concept of setup and hold time. What all of that translates now into is something about our so contamination delay, propagation delay, coupled with the setup and hold time and the contamination and propagation delay of flip-flops together, say begin to give us insight into how fast a sequential circuit, a finite state machine may run or not run. Okay, so this is what I was covering towards the end. So I had this example that let's imagine I have a state machine which has 2 flip-flops, so it's 2 bits of state, and then the combinational logic happens to have 2 modules. One I call as min, one called max. They correspond to the maximum propagation delay and the minimum contamination delay. And then we tried to develop what constraints the circuit has to satisfy. And one situation I had was the following. Yeah. So let's imagine that a clock edge came and this upper flip-flop toggled, its output A changed, and the effect of this A will propagate, go through the max logic, and arrive at the lower flip-flop, which has this input B, and then at this place it has to meet the setup time requirement. So what's happening is from the clock edge, A will change as much as TDCQ after that. That's the delay through the flip-flop. Wires we are assuming have no delay. Then it has the delay of this max, so that is TD max. And all of this should add up to a clock period minus the setup time, because I have to meet the next clock edge before the set. The signal B has to become stable. T sub S setup time before the clock edge. So clock period minus T sub S must be greater than this, or which equivalently translates into is clock period must be greater than TCQ, which is the propagation delay of the flip-flop, plus TD max, which is the maximum propagation delay through my logic, plus T sub S, which is the setup time. And what this basically says is that if I have flip-flops with large setup times, or if I have combinational logic with large delays, then that limits what is the smallest clock period I can have, or equivalently what is the fastest clock frequency I may have. So clock frequency is determined by this constraint. If I get back a circuit and it doesn't work, it's because somewhere in along some flip-flop to some other flip-flop, this constraint is being violated. All it takes is one pair of flip-flop to see a violation of the corresponding constraint. So what we have to make sure is that every path in my circuit which starts at a flip-flop and ends at a flip-flop is such that the delay through the flip-flop plus delay through that circuit plus the setup time is less than the clock period. And there would be one such path which is going to be the most critical. That is the one which we call as the max. So usually it is one path which ends up dictating how fast my circuit is. And then if you are trying to improve the clock speed of the circuit, you need to somehow focus on that path. You need to bring it down. So if you look in a circuit, I'm going to come to your question. If you look at a circuit, there are many paths, like, right? I mean, if I have, let's say, n flip-flops, then I may have as many as n square paths of that nature, which start at a flip-flop and at a flip-flop. And one of those paths is going to be critical. In a well-designed, what would be the hallmark of a good design? Should all paths be the same, or is it that I have one path which is an outlier and is very high? Like, what would you aim for in a good design? All the same. All paths should be short and equal, right? I mean, if I have a spread, that means I have bottlenecks, and those bottlenecks you are going to address until they become similar to something earlier. So the trick to speeding up a circuit is to chase these outliers, improve them until essentially everything becomes equal. Question?
So since most clock things like only care about the rising edge, there's theoretically no requirement that your falling edge is some distance away. Right?
Not in the type of designs we are pursuing. There are circuits where falling edge may get used. There are circuits where the edge doesn't matter, and it's the duration of how high or how long the clock was high or how long the clock was low matters. You can translate all this theory into those contexts also. We didn't do that.
So does that mean that if you had a very narrow clock edge, or your clock was very narrow,
Pulse was very narrow.
Yes. We would ignore like the falling edge violating.
In our design, falling edge doesn't matter. Okay, as long as falling edge is after the rising edge, even if it is 0.001 femtosecond after it, that's fine. Okay, from a purely theory perspective, of course, physically it's not going to be possible. There's going to be something, but we do not care about the falling edge. But you can, for example, imagine I can give you a spin on this where I say, this flip-flop is rising edge triggered and this flip-flop is falling edge triggered, for example. Then what would happen? So let's take that example. Okay, let's imagine. So I think thanks for a good problem. Okay, so let's imagine that this guy actually was not getting. I modify this one so that it is negative edge triggered. Assume. Let's say that's the case. How would you modify this constraint now? Did everyone understand the problem? Firstly, okay. Currently, I had both these flip flops being positive edge triggered, and therefore the whole circuit had to settle before the next positive edge out here. The variant that he proposes, let's imagine that I have negative edges also. So let's imagine that this lower flip flop was negative edge triggered. Okay, so what constraint would that impose now?
Would it just be holding?
Hmm?
Would it be make it holding time?
No, nothing to do with hold time.
You just add how long it's high for.
So I guess instead of TC, remember this guy is going to have its own setup time, but it's going to be for the falling edge. So that means that from the moment the rising edge came here, I have to finish all of that work, setup time before the falling edge comes here. So instead of TCY, I'm going to write the duration a clock is high. Okay, so it will just modify out here. Any questions from the center room? Very quiet on this side. Okay, so if this kind of violation occurs, you really have two choices: go and fix your design to reduce the length of the critical paths, or more easily run the chip at a slower clock. Or is there any other choice from those of you who were at the last lecture? What else can you do? So I have a chip. It's not working at. It's supposed to work at 2 gigahertz. It's not working at 2 gigahertz. What can you do? Come on, you guys. You guys were asking a lot of questions. Huh?
Say that it works at a lesser rate.
1.5 gigahertz and call it a day.
Yeah.
No, I still want to run it at 2 gigahertz. Cool it, right? Put it into liquid hydrogen or whatever, something, right? I mean, so point is that chips run faster at lower temperature. Okay, this in some very newer technologies that's no longer true, because what happens at absolute zero? Everything stops, right? But the thing is, generally speaking, heat running chips hot results in the delays of the gates, namely TD CQ and TD max going up, and therefore that limits your clock. Okay, so if you want to run chips faster, you cool it, which is why the overclocking community kind of puts stuff into Freon and whatnot. Okay, so you have those options. Hold time constraint, which is the other one, which is a nastier one. So hold time has to do with a contamination thing. So the idea is the following, that the lower flip-flop changed. Okay, the clock edge came and its output changed. This output raced ahead through this short path, this min guy, and it reached the next flip-flop, the upper flip-flop, so quickly that we are still in the hold time window. Okay, so what's happening is that, let's say my hold time was 5 nanosecond, and let's say the delay through this flip-flop through, plus the contamination delay through min was less than 5 nanosecond. Then what's happening is that clock edge came and the C changed and D changed, and the change in D has happened so quickly that I'm still within the hold time interval out here, and that's going to be bad. So what it basically says is that the hold time must be less than whatever is the fastest delay I can see, the contamination delay from the flip-flop output of the flip-flop to the input of the or from the clock input to the input of the flip-flop. So TCCQ, which is contamination delay of the flip-flop, plus TC min, which is the fast path through my logic, all of that should be greater than T hold, because if it's not, then I'm going to see a hold time violation. Okay, and this is something we cannot fix by slowing down the clock. So questions then were, what can I do for it? Okay, so I'll repeat that question now. So how can I fix this thing? So let's say you find this violation.
Add delay.
Add delay where?
In the CPU.
In where?
In the C.
This guy?
The wire.
The wire. So you basically boost up the delay out here. Okay, you basically artificially add maybe some buffer or something like that out here. Okay, to do it. Can you add the delay anywhere else? Let's say instead of adding a delay on this line, can you add a delay at a different place and have a similar effect?
You can delay the clock.
Which clock?
So the clock that
But if I delay both the clocks, nothing changes.
you delayed the clock going into the top flip-flop.
Clock going into the top level. That will worsen the problem. Right? I mean, if I put it into the top level, that means I have shifted my hold boundary even more. So you delay this bottom clock. No, hang on a second. Yeah, you delay the bottom clock so that I shift everything so that by the time this reaches out here, it has met the hold time.
Wait, why?
Okay. See, our problem is that our change is arriving too early.
Right.
So I need to delay the change. So I delay the change by making sure the change starts later. Right? By making this change initiate later, then I will make sure that, so basically the suggestion, so I can either add the delay to this block or I can add the delay just at this wire, one of the two.
If you're going to delay the bottom clock, isn't that basically like making it rising edge instead of falling edge?
No, we are still going to be on the rising edge only. It's just that I have the rising edge that this guy will see come a little bit after the rising edge of this guy. Right? So we are not changing the behavior of the flip-flop. So it could be that the top guy sees a clock like this, and the bottom one, instead of seeing the same clock, sees a clock which is a little bit later. Okay. In fact, I can eliminate my hold time problems entirely by making this guy equal to be T sub H. Right? Then I will never have a hold time violation. Of course, the problem is it's never possible because maybe then if I do this, then maybe I will have a problem between this flip-flop and this flip-flop. Okay, so it's very hard to do these delay games very cleanly.
So if you said like if you add a buffer, are buffers pure delays like frequency independent delays?
Digital buffers basically just delay all the edges by a certain amount.
Is it possible that like you're switching so fast that you violate the internal status and hold?
It's possible.
Okay.
It's possible, but so you have to make sure that your buffers are designed to be fast enough from that perspective. Yeah. Now, hold time is problematic because if you get a chip back with a hold time violation in it, there is nothing you can do to fix it short of redesigning the chip. Okay, because the only solutions we have come up involve adding delays, which means redesigning the chip. Whereas for setup time violation, I had the option I can just run the chip slower or run the chip cooler. Okay, but not for hold time. So let's look at some examples. So we are given flip-flops where delay, propagation delay, contamination delay, and setup time are 150 picosecond. Hold time is 250 picosecond. Delay through the max block is 850, and delay through the min block is 100. Is the hold time constraint met? So if we go back, hold time constraint said the hold time must be less than contamination delay of the flip-flop plus contamination delay through the logic. So that in our case means 100 plus 150, 250. So is hold time constraint met? Well, it is 250 plus, sorry. So so it's basically saying TH must be less than T contamination CQ plus T contamination min, which means 250 should be less than or less than equal to, okay, yeah, it's fine, for it to just meet. So TCCQ is 150 plus TC min is 100, which is 250, so our hold time constraint is met. Okay, what about our minimum cycle time? That is the fastest clock. Anyone help me out? So this is a straight application of the formula. Anyone? How fast can I run the circuit? Huh? What was the formula? Come on, guys, you have the slides, right? What was the formula for minimum cycle time?
TCY is greater than
TCY is greater than,
contamination.
no, not contamination,
Propagation.
propagation delay. So it would be TDCQ plus TD max plus setup, which is equal to TDCQ is 150 plus TD max, which is 850 plus setup is 150. So it is 1150, which is some, I don't know, 900 megahertz or something like that. Okay, so that would be a clock. Other kind of problems. So let's imagine I give you a flip-flop again with some setup hold time characteristics, which is used to implement state register for FSM. And then again, for the next state logic, I give you the delay and propagation delay and contamination delay. And then the question may ask you for some other variable. It may say, how much setup time and hold time slack do I have? So slack means how much freedom I have. So what I mean by that is how much I could increase the setup time, or how much can I increase the setup time, and how much can I increase the hold time and still be viable. Okay, and it says operating at a frequency of 1 gigahertz. Now obviously hold time does not depend upon the frequency, setup time depends on the frequency. So let's try this problem. Let's do our hold time one. So again, hold time basically says that the T hold must be less than, come on, help me out. What's the formula? So decontamination of the flip-flop TCCQ plus TC min. Okay. Now what is that in this case? So TCCQ, I'm looking at 60. TC min here 50. So that's 110. And TH we are given as 40. Right? So unless I messed something up. No. Okay. So the slack out here is I can keep increasing the TH until 110 and I'm still okay. So the slack is 70. Okay. So this is independent of the frequency. The other constraint is dependent on the frequency. So at 1 gigahertz, what is the clock period for 1 gigahertz? How much? 1000 picosecond. Good. So 1000 picosecond must be what? Less than, greater than what? Must be greater than. Okay, so let's fill the numbers out here. It's going to be the propagation delay of the flip-flop, which is 60, plus maximum propagation delay through the circuit, which is 800, plus setup time, which is 50. Okay, so that becomes 910. So I have a 90 picosecond of slack on this one. I can increase the setup time to 140 and still meet my frequency requirement. So the nature of the problems out here, and in the homework I have several, they basically, I mean, you have a bunch of variables which are constrained, and I can give you some and ask you about one of the others. Okay, that's basically what's happening in these problems.
So in reality, when these values are given, are these going to be worst case or typical values?
Worst case. Worst case, so these values depend upon temperature, they depend upon manufacturing variations, and also they basically will say across a temperature range and across the chips we are selling you, this is the worst case. Okay, and oh, by the way, the third element is how old the chips are. So the aging is another aspect. So they'll say that look, we are using it in our desktop computers, lifetime is going to be, I don't know, 6-7 years. We are going to be conservative 10 years, so we are going to calculate all the delays as if the chips were 10 years old. Okay. How do you think they test for these things? Total aside. How do they know what's a delay 10 years from now? I mean, Intel is not going to make the chip wait for 10 years before selling it, right? I mean, they don't do that. So what do you do?
you would like make it really really hot and then run it then.
Right. You make it very, you stress test it by increasing the temperature and feeding them lots of input changes. They age because they see signal changing. Okay, so you just and stressing the sort of increasing the temperature also ages them faster. So you can do that, those games. Okay. Oh shoot! Did I? Yeah. Okay, this was correct. We already covered this one, but just wanted to mention that it's possible that clocks may not come on the flip-flop at the same time. So thus far we were talking about, in one of the earlier examples, I had deliberately inserted a delay. But usually these delays naturally exist, because what may happen is I may have a flip-flop at one part of the chip, another flip-flop in a different part of the chip, and I'm distributing the clock to them through some wires, and these wires have delays. Thus far we are thinking of wires as some idealized zero delay entity, but in reality wires have delays. I mean, firstly, speed of light. Nothing can travel faster than speed of light, but that aside, these are electrical signals. Wires have capacitance and resistance, and therefore the edges are going to rise slowly. So you have these kind of effects coming in. So let's say I have this kind of a skew present. This is called skew. So the clock at the upper flip-flop is arriving a little bit later than the clock at the lower end. So what implications would it have? Well, since the clock is arriving later out here, it is bad for me because it eats into my clock budget now, right? Because my critical path was upper flip-flop, going through this max, arriving at a lower flip-flop. So if the upper flip-flop is triggering late, I have already, the amount, this TK is already subtracting from the time budget I had, because I still have to meet the setup of the lower guy. So this equation says clock period is greater than TDCQ plus TD max. So TDCQ because of upper flip-flop, TD max through this guy, plus TS, which is a setup time, plus TK because we started late. Okay, so TK being high is a bad thing for us. TK being negative is going to be good, because TK being negative means that the lower clock is arriving later, and that's going to be a good sign. But if TK is negative, then my hold time runs into problems. So if you look at the hold time, so again, sticking with this TK, what's happening is that our hold time violation was because from the lower flip-flop, we were contaminating the upper flip-flop. So we start from the lower flip-flop, go through TC min, and we hit this guy. And we want, so originally formula was TH is less than TCQ plus TC min. So my shortest delay should still be greater than the hold time. But if I'm starting, well, which way should you look at it? If the upper flip-flop's clock has been delayed, then in effect that has eaten into my hold time. So there's a negative term out here. So if I increase TK in this example, then if I increase TK, then my hold time problem is getting worse, because I may violate the hold time, but my chip is going to run slower. So, but the other way can help us out here. So, clock skew is always present, and you have to factor it in. And again, when they measure these things, they will look at what is the wiring delay and kind of factor these things in. Wiring delay to the first order is going to depend upon how long the wire is and how thick the wire is, right? I mean, thicker the wire, less resistance, more and if the wider the wire is, more capacitance. So all those effects kind of come into play, which affect the delay. So again, relatively well understood things, but one has to factor these things in. Okay, so you can repeat these examples with the skew. I'm not going to do that. So just straightforward applications of the formula. If the skew was present in the other leg as opposed to here, then you can think of it, a skew of TK here is the same as a skew of minus TK in the other clock. Okay, I mean, it's just relative to each other. Okay, so let's look at this guy. So is the hold time constraint met? Is the minimum cycle time? Again, you apply those formulas. Let's see this. So firstly, let's start out with, so what we see out here is a bunch of registers there is a full adder out here, and let's start with the simplest question. What does this FSM do? This sequential circuit, what is it doing? Anyone? This has nothing to do with this lecture even, right? I mean, I'm just giving you a circuit. What is it doing functionally?
We're just counting up.
Hmm?
We're just counting up.
So at any given point in time, so I have an adder out here, right? This is a regular adder. One input to the adder is whatever my state is, right? What is the other input to the adder?
1. Isn't that what the carry in is?
But what about other bits?
Oh, okay, so it's adding it to itself plus 1.
Is it adding it to itself? No.
2 times.
2 times itself, because shifted plus 1, right? So it's doing x plus 2x plus 1. Yeah, right? I mean, let's say, oh, I'm sorry. Okay. This is 0 out here actually, so I'm wrong. So it is actually doing x plus 2x, so it's doing 3x out here. So, okay. If I had a 1 out here, then it would be 3x plus 1. If I have a 0 out here, it's just 3x. Okay, because the other entry to this thing is just everything shifted. Okay, which is basically multiplying by 2. Okay, so now assume for this full adder, I give you the contamination delay and I give you the propagation delay out here. So minimum TC between flip-flops, minimum contamination delays, the output can go and change this thing, right? I mean, the flip-flop changes, its output can go through full adder and come back out here. So contamination delay between any two flip-flops is going to be 10 picosecond, and the propagation delay, what may happen is that the lower flip-flop changes and its effect kind of percolates throughout here, percolates through 16 of these, and then affects this flip-flop. So this path, imagine this path. I go like this. This path is the longest path I have, and it is going through 16 of these stages, and each in the worst case is 30. So I have 480 picosecond delay possible. Assume a D flip-flop for whom contamination delays and setup and hold time are given. Is hold time constraint met? So what was the hold time equation again, guys? So TH has to be what? Less than, greater than, less than contamination of the flip-flop, which is 10. No, what's the contamination of flip-flop? Okay, yeah, 10. Plus the min delay, which is 10. So that's 20. And T sub H was given to be 10. Okay, so we are happy out here. Okay. What is the maximum clock cycle time? So clock cycle time T sub Y is greater than, so we look at propagation delay of the flip-flop, which is 20, plus the maximum time, which is 480, plus the setup time, which is 20. All of that translates into 520. Hmm?
Is this the minimum?
No, all it is saying is a clock. What is the minimum? Okay. What's the minimum clock cycle? Okay. So I can come up with the clock cycle equation. Okay, 520. Can a skew of 20 picosecond be tolerated? Okay, so now we are saying, let's imagine that the clocks at these flip-flops may not come at the same time. They may be as much as 20 picosecond apart. So could that be tolerated?
Yeah, when you have like 16 of these things, when you say skew 20 picoseconds, do you mean between like the largest between any two of them?
Any two. So I take two. I'll pick any flip-flop and pick two flip-flops, and their clocks will not be more than 20 picosecond apart. Okay, so the question is, can a skew of 20 picosecond be tolerated? Now you have to worry about both the hold time and for the hold time case and for the clock period case. So for the hold time case, again, if you kind of go back, so it was T hold was has to be so T hold has to be less than this, but then we had the skew term coming out here, and the skew term was subtractive out here. Okay, if you recall, this is what we had. Okay, so if I'm looking at the whole time, 10 picosecond, less than 10, okay, so that was fine. But if I have a TK of 20, then the right hand side becomes 0. And then we are saying 10 is less than 0, which is obviously not going to work. So can a skew of 20 picosecond tolerated? Not really, because we end up violating the hold time constraint. Okay, so so how much skew can be tolerated? Looking at this, I want 10 less than equal to this, so the maximum skew I can tolerate is 10 picosecond. So that basically means I have to make sure that whatever wiring I have for the clock does not make sure that the clock edges reach within 10 picosecond of each other at the various flip-flops. What can one do? Redesign the flip-flop. Oh, go ahead.
Wait, so can you repeat the equation? So isn't the assumption here that the skew will be like a delay and not an advancement?
Well, so we have to consider, so here when we are saying skew, it means it can go either way. Okay, so if I pick two flip-flops, the skew can range from this guy being ahead to this guy being behind. I have to consider all possibilities.
So the skew range is
minus 10 to plus, implicitly minus 20 to plus 20 for any pair of flip-flops.
Okay, so a skew 20 picoseconds means plus or minus 20?
Right, unless I were to actually show you out here that, okay, the skew is occurring in this clock physically out here. Okay, in the absence of that, each direction is fair game. Okay. So redesign the flip-flop, reduce the clock skew. None of these are practical really. Add logic, which increases the delay. Okay, so that was another option. I'll just complete. Okay, and yeah, okay.
Quick question. Going for the full adder and minimum contamination delay
Flip-flops is 10.
How do we get that?
Here, look at this part. So let's imagine the bottom flip-flop changes. Okay, the effect of that can go through this full adder and feed back out here within 10 thing, because I'm just going through one full adder.
So it is considered just one.
Yeah, so remember, again, the rule is I have this combinational logic, and I have to find what is the contamination delay through it. Contamination delay through it is the minimum of all the contamination delays that exist from any input to output. So from corresponding bit to output, the contamination delay is 10. So that's what we have.
So the contamination delay for the system is the minimum of any of the units, because
when they are in parallel, right? So for series, it is the sum of the minimum contamination delays, and for parallel, it's the minimum of all the contamination delays which are in parallel. Okay.
Because in the case of the sum, you could have your intermediate states be somewhere in the cascade.
Correct, but that doesn't matter, right? Again, this full adder has 16 inputs and has 16 outputs. Okay, my minimum contamination delay is between some pair of these. Okay, and specifically between input 0 and output 0, the contamination delay is 10.
Okay, so even though there is a cascade, we're concerned with the total output, the parallel output of the system, so that's why we're...
Well, remember, contamination means the earliest any of the bit of the output begins to change.
Yeah, But if the output were just the highest order bit.
Okay, if the output was just the higher order bit, okay, so let's modify this thing. We basically say, hey, I don't care about all these intermediate bits. I only care about the output bit. What would be the contamination delay?
Would not be the sum
Sum of what?
of the
Contamination delay. So what would be in this case? 160, right? Okay. Now, of course, in this system, I am making use of all the other lower bit output also, which is why the contamination delay is 10.
So for the skew, how do you know whether to be plus TK or minus TK for TCYFT?
If I don't show anything, then that means that, so general question, can a skew of 20 picosecond be tolerated? Means that it's magnitude. It can go either way. Okay, so if I pick two flip-flops, one could be ahead by 20 or be behind by 20. You need to analyze for the entire thing.
And so that works if they are in parallel, they're in series.
No, it's nothing. For flip-flops, it's nothing to do with parallel and series. Okay. What is the wait.
Wait, sorry. So is the contamination delay the sum though? Because you do have a register at the top, the highest order bit. So wouldn't that be the first thing to modify the output if it changed state?
So contamination delay would be the sum, because what will happen is I'm starting out here, right? And well, hang on a sec. What about the inputs? Do you care about the inputs?
If the inputs all could change.
If inputs all could change, then the contamination delay would be 10.
Okay.
Okay. If only this input mattered,
Okay.
then it would be 160.
All
Okay. Is it clear?
Yeah.
Okay. Yeah. So you have to be very precise what the inputs and the outputs are in this case. Okay. What is the effect of adding logic with 10 picosecond before each D flip-flop? So what we do is, at the input of each D flip-flop, we put a buffer of 10 picosecond contamination delay. What happens now? So what would it affect? So my hold time equation will certainly change, right? I have an additional component on the right hand side, and in particular now I can still tolerate a 20 picosecond skew now, right? So hold time equation would look something like this. So that would be met, because we were running into problem just because of 10 picoseconds. So I've added, but adding this delay before each flip flop is also going to affect my clock cycle. There is going to be some additional input out there. Okay, and I guess I should have set 10 picosecond delay before each flip flop, so my clock period will go up also. Okay, so fixing a problem can create problem elsewhere. One has to kind of factor these things in. So, in summary, delays in digital systems come in two categories: propagation delay, contamination delay. For combinational logic, it's the case, and then for flip-flops, we measure it from clock to the output. For flip-flops, we have additional constraints which are called setup and hold time. And because of artifact of the way we package these flip-flops, that is, it may be some flip-flop plus some logic, we may have a setup time and hold time which are negative. Okay, but one of them can be negative, the others still have to be positive. The sum of the two still has to be positive. Cycle time is determined by the maximum delays, and correct operation, which is the hold time, also depends upon the minimum delay. So we care about both how slow the circuit is, and we also care about how fast the circuit is. Clock skew affects both, and clock skew refers to the fact that my clock distribution is not perfect. Okay, I mean, just physically think of it this way: clock source is located at some place. Flip-flops are located at different points in space. Just because of speed of light, the signal will take, or whatever, just travel time, the signal will take different amount of time to reach the flip-flops. So it's almost impossible to design something where I can make sure that the clock edges are coming at the flip-flops exactly at the same time. It's not going to happen. It's just can't design that way. So because of tolerances in manufacturing and all, you are going to see these effects where the clocks are arriving earlier or later at some flip-flops. And you actually don't even have control over it, okay, because clock delays also depend upon resistance of the wire or capacitance of the wire, which again depends upon manufacturing. So it could be on one chip, flip-flop 1 is ahead of flip-flop 2. On another copy of the same chip, is the other way around, which is why, again, for skew, we have to consider both plus and minus signs. Okay. So all of these factors sort of come into play. So what happens when we violate setup and hold time? So I had mentioned earlier that that leads to, so basically what it means is if data changes within this time window, bad things happen, and those bad things can look pretty nasty. So this, just to kind of show you what can happen. So this is a flip-flop's output at the bottom, and the signal looks like this. Okay, it's just basically, it's just all, it can go into oscillatory behavior, it may just hang at some voltage, and it can hang there for long time. Okay, so this is called metastability failure, and when it happens, the effect of it can linger for a long time. Okay, so any questions on this before I go ahead?
What's happening here?
Okay, so we violated the setup and hold time. Okay, and this is the output, the bottom one, and instead of signal going cleanly from what was supposed to happen, this was my input. This was my input. The input was going from 1 to 0 back to 1. The output, we would have expected to have some behavior like that, except that since we violated the setup and hold time, we are seeing that the signal is looking just totally rubbish. Okay.
So it's basically supposed to be like a delay element. We're supposed to see the same signal as on top, but delayed by a little bit.
It would be a signal which would have cleanly transition to low and then back to 1. Okay, but it's not. Okay, so it's getting into this analog mode basically, and so it started out oscillating, and then its frequency appeared to have changed, and all sort of weirdo stuff which is happening. So when flip-flops fail with metastability, essentially they are no longer behaving like a digital logic. Okay, they are behaving in an analog way, and in more advanced courses you will learn, if you decide to go into circuits, you will learn about like what happens. There are so metastability fundamentally is happening because we are violating this time requirement. Now what we saw in this lecture is that by carefully designing the circuit, I can make sure that any output of a flip-flop that we have in the design meets the setup and hold time requirement by the time its effect reaches at another flip-flop. So question for you, is it always possible that all signals in my circuit will meet setup and hold time requirement? Are there some signals where fundamentally you cannot ensure setup and hold time?
Your input. So if you have
Input where? Like what?
if you have an external input.
External input, right? So let's say I design a digital system, and let's say there is a sensor out there which whenever the light shines on it goes from 0 to 1, whenever the light turns off goes back to 1 to 0. And if I'm feeding this signal into my finite state machine, then its 0 to 1 and 1 to 0 transition depends upon whosoever is shining the light. Could be sun, could be room light turning on. So external signals are impossible, just in principle, impossible to arrange for them to meet the setup and hold time requirement. So what do you think can be done?
Buffer and edge align the input.
Yeah, buffering is not going to. If buffer just adds the delay, then you're just shifting the problem. It's still going to happen.
But like preventing like rapid transitions from propagation.
It's not about rapid transitions. It's the fact that that 1 0 to 1 edge can happen at, right. I mean, so let's look at it this way. Okay, so I have a system, synchronous system, in which there is an external signal, let's say coming from a sensor. Okay, internally to the system, there is some flip-flop to which this signal's effect is going. Okay, this flip-flop is a clock. I have to make sure that any edge on this signal, any changes in this signal, do not happen in certain time window. Okay, now let's assume the case that the external world is a totally independent entity. So the changes in this sensor value can happen anytime. In particular, they could be uniformly distributed in time over my clock period. So if I were to just focus on, let's say, a clock period, then the probability that the signal is going to change is uniform out here. Delaying this signal is not going to tell me anything, right? Delaying that is not going to solve the problem at all. Go ahead.
And apply like a low pass filter.
No.
Can you just have a clock in there and then the sensor starts the clock? Or?
No, so in principle, this is an unsolvable problem. Okay, it's not. I'm asking you for a solution because it's unsolvable, right? So what is done is the following: that they create these specially designed, what are called as metastability hardened flip-flops, and what they internally are is they are actually two back-to-back flip-flops. And one of them is operating on a clock and the other one operates on a clock which is slightly after it. So it's like edges right after each other. And it turns out you can show that something like this, you can reduce the probability of metastability occurring, or that if it does occur, it comes out of it sooner. Okay, you still do not eliminate. Okay, but as long as you can reduce the probability of metastability to be longer than Windows crashing, which is not asking for much, you're okay, right? I mean, so something of, but you get the point, right? I mean, there are other things that cause the system to crash or to be shut down or whatever, right? So as long as I can reduce this probability to 10 to power minus 12, minus 15 or whatever, and therefore other things are going to bring the machine down. That's good enough for me. Okay, so you create these hardened flip-flops. There are other things which bring machines down. Okay, so OSs bring machine down. What else? What else crashes machines? Power surges, power outages, right? What else? Alpha particles from nature, cosmic rays, they can flip a bit. Bad things happen. There are all these other sources which cause problem. Rare events like that, yeah, sure. Anyway, so point is that metastability cannot be removed. It's an art. It's just part and parcel of life. That if I'm observing something, then and I'm trying to sample it, it's fundamentally impossible for me to arrange if the two parties are independent to arrange that I will not sample when something is changing. But I can just kind of play. I can try to reduce. Try to harden against that, against the bad effects. But any case, when it does happen, you will see that the signal is no longer digital. It looks like this weird thing. Okay, so I have a little quiz for you guys. Again, extra credit.